All right, so good afternoon. The first talk after lunch will be by Sepehr, who will tell us about lower bounds.
All right, thank you. Thank you again to the organizers. It's great to be here. And thank you for coming after lunch. I tried to not put you just there. So, all right. Good. So I'm going to talk about recent or new advances in multipass graph streaming lower bounds. Again, at any point, just stop me, ask questions. I was given two options, decide between survey and tutorial, and I was thinking between them. I'm going to do the tutorial part, so this is really not going to be a survey-ish talk. And the reason is that I feel like I've given a couple of talks which are quite survey-like on the same topic. If you wanted to look, there is one on Banff workshop from a year ago. This HALC last year. There's this article also. I mean, Andrew kindly called it a survey. It's still not at the level of a survey, but it mentions the thing. So if you want to get caught up with what has been happening in this area, maybe you can take a look at these. And I wanted to mention an actual survey on graph streaming algorithms if you want. Andrew has one from 2013 that is covered the classical part at this point. I think 14 actually. No? So I'm going to. Okay. All right, so this will be the plan for the talk, and yeah, I learned I'm going to write the references and refer to these instead of trying to come up with them on the fly. Good, all right, let's start. So we are talking about graph streaming lower bounds, and let's define the graph streaming model first. This graph GVE. For the purpose of this talk, I want to just think of vertices as being numbers 1 to n. I know them pretty well. There's no uncertainty about the vertices. Edges are the ones that are coming in some arbitrary order. I have no control over this ordering that is coming to me, and I have an algorithm that is going to process this stream multiple times. Okay, so it's going to read the edges in this order, decides to do something with that information, then it's going to get to see the edges one more time and few number of passes over the data, and then at the end has to output the solution to the problem. And the space of the algorithms, we are going to just fix it to be the semi-streaming space that Andrew mentioned as OT-log. And there are good reasons to focus on this one. I will not get into that. But the very quick summary is that below this, most of the things we are talking about are super hard. And above this doesn't seem to dramatically change the power of the algorithm. Not always. Okay, good. All right, so very quick reason why do we want to look at the streaming lower bounds. And this is why a streaming lower bounds. I'm not talking about why lower bounds in general. So there are all the good reasons to look at lower bounds in general. But why streaming in particular? One reason, which is again not entirely unique really, but it's very closely related to the algorithms as well. As you have seen, it happens very, very many number of times in the streaming literature. People have been trying to prove a lower bound for some problem and then figure out, oh, actually, there's like those insights give you an idea to how to come up with an algorithm or vice versa. It's one of those areas you can play, like you can do upper bound and lower bounds at the same time and gain lots of intuition by like moving between these two. I think that's pretty neat here. The other reason is good is models related to a streaming. There are lots of models that we know, and you've heard about them in the last couple of days, MPC, for instance, in particular, sketching, etc. They're very closely related to a streaming model. In some of those models, we really have no tool to actually prove lower bounds. Okay, let me give you an example. The MIS maximal independent set, let's not worry about what it is, we'll talk about it a bit later. But for instance, MIS is, people have studied MIS across different models. For instance, in the MPC model that people talked about, there is an order log n round algorithm for this problem. This algorithm is not that. This algorithm is the streaming algorithm for the same problem. Okay, so there is also a semi-streaming algorithm, order log and rounds or passes now that solve the same problem. So it's literally the same algorithm that is also being used in the MPC model to solve the problem. Now, I can ask this question, in the MPC model, can I prove an omega log n round lower bound? If you were here yesterday, as Arthur was saying, or you have heard of it, it's like as hard as proving some circuit lower bounds. We have no idea how to prove. Okay. So in MPC, we cannot prove the lower bound. But now we can prove, for instance, that in a streaming model, at least, this is the best you can do. Okay. This is going to tell you a lot also. These techniques that we've been using in the MPC, for instance, they're not going to be able to extend those things at least. It means you have to come up with fundamentally new idea, which is not as streaming friendly in some sense to solve the problem. And so because of this, I think these are some additional bonus reasons to look at lower bounds in the streaming model. All right, so now on top of all this, I think the main reason is, which is the same. It's quite fun, actually, and for that reason, it's related to two very nice aspects. It has a very good combinatorics. It has a very nice information theory part. I hope to show you a bit about them, and to prove these lower bounds, especially when you're talking about semi-streaming algorithms, you have to do a lot of different combinatorial things, which is interesting. You still also have to do a lot of information theoretical things to get the lower bounds. So as a whole, it makes it interesting. Good. All right, so that was all my introduction, everything for this model, why you may want to listen to the next 50 minutes of the talk. Okay. Any question? So now suppose I want to prove a lower bound for this type of algorithms, okay, for some problem, let's say MIS, for instance. How would we do that? There is a very standard idea to do this, and that's going through communication complexity. Really, my plan is to go through something such that after today, maybe you can pick your favorite problem in a streaming model, if you have one, and try to just use these ideas to prove lower bounds for it. So I'm going to go through them in details. So communication complexity, you can use it to prove a streaming lower bounds. What does this mean? So think of this setting. I have Alice. There's this graph G. I have Bob. The edges. Some subsets are given to Alice, some subsets are given to Bob, maybe arbitrary partition between them, okay? And I'm going to ask them to solve some problem over G, okay? But neither of them have the entire input, so they have to talk with each other. Okay? And communication complexity is asking you, this is communication. And then CC of a problem P is minimum number of bits you need to solve this problem, okay, for any input. Does this make sense? Okay. So why am I bringing this up? It's because it's very simple observation that started, I mean, at least as early as when people defined a streaming model.
It's an arbitrary partition, A and B.
Yes.
So it's worst case. Okay.
It's worst case. You can always talk about what happens if I randomly partition. It's a graph if I based on vertices partition, and that will have different implication in the streaming.
The way you're saying it's not just a partition of the input. These are just arbitrary information that you're giving to each player.
No, partition edges of the input.
It's a partition.
Yes, it's a partition of edges of the input.
Okay.
So now suppose I have a streaming algorithm for this problem P. For instance, I can check whether my graph is connected or not. Okay. What does that imply here? It means that, look at, Alice is going to treat her first part of the input, her input as first part of a string. Okay. She's going to run that streaming algorithm over that. When it is finished, it's a streaming algorithm. It has some memory content. No? She's just going to look at that memory content and sends it over. Now it's Bob's turn. Bob, how does a streaming algorithm work? It reads the input in one way. Bob doesn't need to ever read these things. He already has the memory content of the streaming algorithm. So you can just continue running it on this part of the string. At this point, Alice and Bob collectively ran one pass of the streaming algorithm. Okay. So now Bob is going to send back the content of the memory. They're just going to play this game. Okay. And what does that mean? It means that if I had a p pass S space algorithm, this is going to give me a, let me just say, order p times S communication protocol for the same problem. All right. So we are all good with this? So this.
These type of things would only prove lower bounds when each side you cannot make, you cannot get a good
Yes, thank you.
flow about the.
You can do almost anything with this. Yes. So no, there are lots of reasons. This is not the good way of proving lower bounds. Okay. There's some reason is that this model is a lot stronger than a streaming model. Okay. The power that Alice and Bob have here is a lot more than what a streaming algorithm can do. Okay. So in reality, when you want to prove the lower bound, you may need to partition it into many players. You may even have to look at it as a branching program instead of communication complexity. There are all those things. But for this talk, I'm going to point out actually an even more important flaw with trying to just use this. Okay. So the problem is this thing. In some sense, all we have to do is to prove a communication lower bound. Okay? And you can do it using reduction to your favorite problems. Here, let's just set disjointness. But it's really not going to work. Okay? Because let me, for instance, look at this problem. Now it's like MIS. Okay? Maximal independent set. Maximal independent set. This is a set of vertices. It's an independent set. They don't have an edge with each other, and it's a dominating set for them. Question?
No, just, can you check if the mic in front of you is turned on? No, not this one. This one.
I think this has some echo, no? Okay. Sorry. Okay, so MIS, find a set of vertices. There's no edges between them, and it's maximal. Okay. It's an easy problem to solve classically, okay? But it's also a very easy problem to solve in communication complexity. Like, what is CC of MIS? Does anyone see how to solve it in this model?
Can you just send the MIS for the first part?
No, I don't. No, that will not work because someone else may have an edge between the two pairs. Yeah. So what you can do instead is the following. Alice is going to look at V1. This is the first vertex. Okay. She's just going to tell Bob, look, these vertices are all neighbor to this V1. She has some of the edges. She knows some of the edges incident on V1. So she's just going to tell Bob that, look, these vertices are definitely not going to be in the MIS. Bob is going to tell her that, yeah, these vertices are also not part of the MIS. Then you add V1 to the MIS. Okay. You will go to the next vertex. Sounds good? In this vertex, you're going to tell, are there any new vertices that are not in the MIS? You're going to tell the other player. Sounds good? And then the other player tell you, okay, these are the other neighbors. So you pick the first vertex here. Then you look at what is the next vertex you can pick. You pick that one. You continue like that. And the communication complexity you get is order n log n bits. You never need to send a vertex more than once. Okay, you know that's not part of the MIS. Does it make sense? I really just ran the greedy MIS algorithm here. In fact, it's not only MIS, it's give you lexicographically first MIS. This is giving you lexicographically first MIS. So pretty easy problem in the communication complexity model. But what was our goal? Our goal is to prove a streaming lower bound. So what should I do? What do we know about MIS in the streaming model?
You can think instead of saying how much communication, you can say how many rounds and how many.
Exactly, we have to get to that. Yes, yes. So here we want to figure out what do we know in the streaming model. For now, despite my best attempt, I forgot to write that reference. Or the log n passes. This is for MIS. And for LF MIS, we know nothing. So there are no algorithms that we know for lexicographically first MIS. And for MIS, we know order log n passes. Okay? Can I use this to prove any lower bound for MIS? No, because I have to bound P times S. Okay? The best lower bound this can give you for a semi-streaming algorithm is nothing. Like a semi-streaming algorithm, S here is O tilde n, and the lower bound here is order n, okay, or O tilde n. So if you want to apply such a procedure, you will not be able to infer any interesting lower bound for either of this problem. It's not surprising, again, as Avishai was saying, this is just too strong. We have to relax it in many ways. And let me just, for this talk, I'm going to look at the one of the relaxation, and that's this reduction. If you look at it, it did not actually, it's not an arbitrary protocol that you get. It involves only 2p minus 1 rounds of communication. Does it make sense? When I did this reduction, the number of times the player talked with each other is 2p minus 1 or something like that. So if I want to prove a communication lower bound, at the very, very least, I have to limit the number of rounds. Okay? And the moment you do that, things will start changing. For instance, this protocol that we saw was heavily exploiting the fact that I have many, many rounds. And if you're curious, if you start looking at bounded round communication complexity, then what you can do is to prove now lower bound. This is this. That proves you need omega log n passes as well. And that's what I'm going to talk about. So you can prove once you start looking at just looking at two-player bounded round communication complexity is enough to prove omega log n passes lower. And for this other problem also, in fact, you can prove, this is the reference for that. 697 for LF MIS, you can prove omega n to the 1/3 now. So a polynomial, this is basically, as Andrew was saying, after log n, really, it means that you really are not going to look at that problem in the streaming model. Okay? So you can prove a very, very strong lower bound if you wanted this very particular MIS. Good. All right, so that's for the graph streaming lower bounds, how you would prove them.
Can you prove it via communication complexity? So you prove that the number of rounds.
If you are communicating O tilde n bits per time.
For the upper bound, is that thing possibly n rounds? The
This one?
Yeah.
No, not you. Like this algorithm
Yeah,
specifically. I think you can create something which is omega n rounds.
But randomizing the order doesn't help you in any way.
Oh, it completely changes everything. The moment you randomize, you get order log n. Okay, but this was ordering was given to you.
So I guess one of the advantages of going through communication complexity is a lot of people already solved the problem you're already seeing.
That's true. Yes, but then my answer is in that case, that problem does not belong to the streaming model. You know, if a problem is communication complexity is high, it's so much harder than it doesn't make sense to even look at it in streaming. Good. So, all right. So let's go on. And by the way, this is not like a new thing that you look at bounded round. This has been happening for years now. One of two good references are these two, 4 and 5, that like at this point, classical results for proving like multipass lower bounds using bounded round communication complexity for graphs. Important. Okay. So now I'm going to, my goal today is to really show you this lower bound. How you're proving omega log n passes for semi-streaming MIs. let's start by proving a one-pass lower bound. One-pass lower bound turns out to be, there are easy ways of proving it, really. And it was proven first by Cormot. Not written anything. And also in parallel in this number 6 separately. Anyway, so let me show you a one-pass lower bound. The version I'm showing you is not exactly either of these two, but it will be more in line of how we want to extend it. So suppose you are Alice. I'll pick some graph, maybe I'll call it H. This is a random graph. Okay, I pick a random graph, random bipartite graph. So it's a random bipartite graph, I'll call it H. Okay. And I copy it twice. So Alice is going to get the edges. So this set of vertices are known to everyone, their partition, etc. Alice is going to get two identical copies of a random bipartite graph, here and here. Okay. What does Bob get? So this is Alice. Bob is going to, we are going to pick a random pairs of vertices, U, V, and the same pair here. U and V is chosen randomly. Okay. So let's look at here. Bob is going to get the following input. For every other vertex connected to the other side, to all other vertices other than U and V. Make this almost click-based. Connect all these extra vertices to the other side. Just do not touch U and V. So it seems a bit crazy. Why am I doing this thing? Now, let me convince you that the MIS of such a graph has a very specific structure. Okay? And the reason I'm doing these two copies, there's this problem with MIS, a single vertex, you can always, like as a person who is finding an MIS, you can ensure that a particular vertex is always in the MIS. Okay? You can just pick it and start from there. Okay, so I'm just creating these two copies so that I have some room to prove the lower bound. So now, so does this make sense? The graph look like there are these U and V that are not connected to the other side. Everyone else is being connected to each other. How does an MIS of this graph look like? Yes, no, not the UV. This UV may or may not have been given to Alice. This is not an edge. This is pair of vertices. Okay, so Bob doesn't put edges here. Bob connects these copies to each other, except for U and V. Okay. Now let's look at this. Suppose you want to output an MIS. Maybe you'll decide to pick a vertex W here. So suppose this vertex W is in the MIS. What happens to this copy? All neighbors of W can no longer be in the MIS. All these vertices are no longer in the MIS. In this copy, the only thing that remains is U and V. In some sense, the moment you pick a vertex from here, W, you will clean out the other copy entirely. Just this pair remains. But your task is to find an MIS. If this is an edge, you have to pick U and V. Sorry, you only have to pick one of them. If UV is in H, MIS has U or V. You cannot have both of them. But you also have to have exactly one of them. Okay? But if UV is not in H, then MIS contains U and V. Does it make sense?
Bob connects the edges on the right side as well?
Yes, these parts, they're all connected to each other. Any vertex which is not U and V, you pick it and you connect it to everyone on the other side. So when I pick W, this copy may get corrupted. Maybe V is neighbor to it. I don't know what will happen here. Okay. But this copy now, U and V remains on its own. Okay. And so you have to figure out this edge exists or not. So that was the combinatorial part. That's easily fixed. How should the MIS of this graph look like?
Should you also like connect the two copies of U to each other or something?
No, you don't have to worry about that. You can do it, but nothing bad will happen. My goal is I look at the vertex from here, and then I just look at what happens to this copy.
So I was saying, if U comma V is not an edge and they're not connected, isn't there a 4-vertex MIS where you take both copies of U and V?
From where you're picking that vertex. So you are worried that these two, so this is not an edge, and you're worried that both of them will.
Both of them and the other two on the left, all 4 is a 4-vertex.
Oh, okay.
Also an MIS.
Does
it matter?
I don't think it matters. Let me see. You're saying this U and V, there is no edge between them.
Yeah.
Okay.
And not to the other side also. So then there's an MIS.
Sure, but so there's no edge between, so you pick both of them. That's fine. No, if there is no edge, you pick both of them. That's completely okay. And if there was an edge, you couldn't pick both of these two.
Okay.
So the promise is that the algorithm outputs an MIS, so then your output you just check, is U and V both in the MIS? If so, then Alice must not have had an edge.
Yes. And you just look at you have to figure out which U and V you want to look at. You look at this W, and you look at the U and V of the other side.
And some of the point is the MIS must always touch U.
Yeah, because maximality will force it to do it. Yes. Okay, so let's not get too much bogged down into exact thing what is happening here, but combinatorially this is okay. And information theoretically, it's also now very easy to say that Alice needs to send omega n square bits. Why? Because from perspective of Alice had a random graph. She has no idea which pair is important or not. Bob is the one that picks U and V. No? So I give you a random graph. I don't tell you which edge is important. And then at the end, you send a message. Then it's Bob's turn to figure out whether some random edge belongs to that graph or not. This basically, Bob can, think about it, Bob can reconstruct what was the random graph Alice had. Okay? So, or more specifically, the entropy of this particular bit has to be small enough such that Bob can output whether it exists or not. And this bit is completely hidden to Alice. So Alice has to basically tell you some information about every pairs of vertices. So she can tell you something important about this one particular pair. Yes, you can just literally reduce to index and be done with this. Okay. So that's a one-pass lower bound. This is it. You can prove a one-pass lower bound. Let me try to extend this to 2 passes. So now we are here. Round elimination. And round elimination is a very general technique. It's not limited to what I'm talking about. But I'm going to show you perhaps one of the simplest example of round elimination in communication complexity, and one of the most classical versions. It's very easy to work with. And this is this. So let's see if this is a technique for proving more than one round lower bound, bounded round lower bound. It basically allows you to prove an R round lower bound from an R minus 1 round lower bound. So I have Alice and Bob. Alice has this input x1 to xk. Bob has I and y. The big problem is the following. There is some function f. The general communication problem that they have to solve is what is f of xi and y. Okay. So there is some function known to everyone. Okay. Alice has a bunch of input. Bob has an index of one of these inputs and y. And your task is to solve this particular function f for the pointer of Bob and the input he has. Does it make sense? I'm defining a problem out of this function f, k inputs, I and y. For instance, in this context, how can we see that? Take f to be the function which outputs 0 or 1 if the bit given to it is 0 or 1. Y can be empty. So f is, you can call it the echo function. Okay, it just outputs, its answer is whatever xi is. Y is irrelevant, so there's no y. Okay. What are x1 to xk? They are whether xi is 1 if there is an edge between the ith pair. That's the index problem, basically. So I can apply round elimination to prove this. Okay. But is the problem definition okay? What is the result here? The result is this very natural thing that either Alice sends omega k bits, or CC is CCR minus 1. What does this mean? Either Alice is communicating k bits in her first message, okay, or the amount of communication the players need to do is proportional to the r minus 1 round communication complexity of computing f. And it's a very, very natural, like, you should expect something like this to be true. Like, intuitively, if Alice is sending a small of k bits, okay, she's not telling you even 1 bit for each of these inputs. Okay? She's revealing very small amount of information about one of these inputs. Okay? Bob picks one of them randomly. And now that Bob picked that one randomly, think about, like, Alice sends a message that does not tell you anything about x. Now is your turn to solve the problem, but you don't know anything. You lost the round without knowing anything. So now you have to spend r minus 1 round and the communication that is needed to solve the problem in r minus 1. Okay? This is important, and these are independently sampled. For instance, this cannot be all the same input, and you expect this.
It's randomized or deterministic?
Go ahead, please. Oh, R is the number of rounds that you, so I'm saying the R round communication complexity of this problem is equal to this. So there was a question. This is randomized also. Like, you can change this thing. It also is true for deterministic and also random. I'm hiding lots of things under the rug. For instance, when you're talking about the communication, the role of these players get reversed. Okay. Now Bob is playing the Alice in 1 round, for instance. There are some changes between the error probability or success probability of the protocol. You have to prove a slightly, like, for a slightly better probability of success, etc. But as a whole, this is the idea. Yeah.
K is a parameter you get to choose in the reduction.
Yeah, you can pick whatever K you want.
Is there any setting you would not set it to the communication complexity or in R minus 1 rounds?
And let me show you. Yes, I'll show you one reason. You don't have the option of picking it exactly what you.
You said that your line, like, so what prevents, like, Alice sending nothing in the first round, Bob sending I, and then Alice sends X.
Yeah, but this is just F. It's a single copy. Okay, I'm not getting a direct sum of many copies. It's just 1 copy. So that's the right protocol. Alice doesn't say anything. Bob tells Alice this was I, and now you solve for I, basically. Okay, and this is communication copy of just a single copy.
So I should think of these X sizes as long, not like.
Yes, they're not bits. They're large inputs. Sorry, yeah, that's a very good point. In general, they're very large inputs. So let me try to use this. If this works for you, this is the best recipe to prove a multi-round lower bound, really. Okay, it's very simple, very clean. Let me try to use that to prove a lower bound for MIS. So I'm trying to do this thing. We created these instances, okay? What am I going to do? I'm going to give Alice these graphs G1, G2 to GK. These are small graphs, okay? To Bob, I'm going to give I, and one graph GB. You know, my goal is to create a lower bound for MIS. What are these graphs? GB is the Alice part of the one round lower bound. It's these two different bipartite graphs. Okay, so this is what the collection of those two bipartite graphs is given to. Bob, what are these things? These are each of them are what Alice would have gotten for this input. Sorry, what Bob would have gotten here for this particular input. Okay, so I'm trying to prove a two-round lower bound for MIS. I'm going to give all these different graphs to Alice. I'll ask Alice to put them all, or like I'll tell Alice how to put them all inside a single graph G. There is one graph that contains this G1, G2, G3, and I copy it exactly as before. I'll pick these graphs. I somehow embed them inside a bigger graph, and we'll talk about that embedding. Okay, and then I copy that graph twice. Good. And to Bob, I'll give this particular graph GB. How does, and what else? There is this index I, maybe this is I. I will connect everyone else with each other between this set of vertices. So now between these two copies of G2, I'll put this graph GB, which is what Alice would have gotten in the one round lower bound. These two are now going to form this 4-layer graph. It's confusing. As in, you're completely right. It's a bit of a messy thing. And also, if you are very seriously confused that, oh, this cannot happen, you're right also. This cannot be true. You cannot do this. Okay, but let me just as in you can do it, you just don't get anything interesting. But what is the recipe? So I'll pick a bunch of graphs. I sample them according to here. Like these are independent graphs. Each of them are what Bob would have gotten in a one-pass lower bound. Okay. I'll pick one what Alice would have gotten in one-pass lower bound. I do this copying business twice. I pick one of those graphs. This is what I tell me. I put what Alice is getting on top of this part, and everything else I connect with each other. Why is this a good thing if the things work out? When you're computing the MIS, maybe you pick a vertex W here. When you pick that vertex W, it will remove all other vertices. The only thing that remains is this G2. Okay. Now that this guy remains, you have to find an MIS of this guy, okay, in the next round. So your goal was to compute MIS of everything. You did some communication. You pick this vertex at the end. This will isolate this particular graph out. So any MIS of the entire graph that you pick contains this MIS of here. So you solve a hard problem here. Good. MIS of the entire graph requires you to find the MIS of this part. This is what this problem was asking you. Find the F of this particular pair. So to find an MIS of the entire graph, you have to find the MIS of this one copy. Yes, you need that, all of that. But this reduction is doing the self-reducibility. So this is what roughly the reduction should look like. Now let's look at the parameters you get from this. Because I told you I'll find an embedding of putting these instances into a graph. What are the numbers I want? So this round elimination tells me omega k. And let's say these graphs are on B vertices. In one round lower bound, I have also omega b squared lower bound. So my lower bound is minimum of k and b squared.
So sorry, another dumb question. So it has to contain it, but you still need to extract the right one from the end solution. The program asks you to solve the
So solving the MIS of this entire weird thing, also that MIS also contains an MIS of G2. And MIS of G2 is F in this definition.
So you still need a little bit more communication to be like, oh, and by the way, I'm going to remove that extra vertex.
So that, yeah, but don't worry about that part. That I'm not the algorithm designer. I'm designing the lower bound. Your task is to give me the MIS at the end, okay? And you have some magical way of doing it. I can look at that MIS and figure out the answer to my problem, okay? Okay, so the lower bound I get is minimum of these two things. What is the property, the bare minimum property of this embedding? If you put this graph here and another graph here, these sets of vertices, they should be induced with respect to each other, okay? So all of this is inside one graph. If this is G1, and there is a G2 that put an edge between this G1, what will happen? If this edge exists here, if your job is to solve the problem for G1, this is an edge from another copy inside this part of the graph, okay? So this induced part of the graph is no longer an actual instance of this problem. It got corrupted. Like, there is some part of the input. The problem is only hard if G2 is actually sampled from the one round hard instance. If G1 is allowed to put a bunch of edges here, G2 will not be sampled from the one round hard instance. So G2 should be induced. These graphs should all be induced with respect to each other. They cannot share edges. They can share vertices, that's okay. But they should not share edges. So what does that mean? Each of these graphs need to have then B² edge slots, okay? If you have B² edge slots, it means that in a graph that has n vertices, you know k times B² is less than or equal to n². Which, even in the best case scenario, k is equal to n² over B². But what is minimum of these two? This is n. Good. This is correct. No, minimum of these two is n. Oh, yes. So the only lower bound we are proving this way is omega n. So this is not useful because this embedding is a very bad embedding. Like, there is no way to embed this thing in a graph. So I already confused you enough, no? There's two more levels. I'll try to do one of them. The problem is I cannot do the more fun one without doing the next one. So I'll try to do it a bit faster. So let me start changing a bit. I'm going to change this one to now doing a slightly different type of round elimination, just a bit. This is like round elimination plus plus.
Like you lost because you picked dependent inputs?
Very good question. So yes and no, okay? The question was that because I picked independent inputs, I lost all the control over how to put these things together. And in some sense, lots of the lower bounds here, like things like some of these lower bounds, we were trying to not pick independent inputs, try to fix it there to make sure you don't put edges, figure out what does the distributions look like. They'll become very messy, okay? I'm going to do something which doesn't involve all of that. I'm going to work with independent inputs, just put a bit more structure over it, okay? So the change is this one. The first part is to change this round elimination, prove something stronger, prove it in some sort of a matrix U. So I'm going to call this x1 to xq. x1 to xq. I'm going to give lots of x's in form of a matrix to Alice. Okay. Then Bob is going to pick a column, and he has y1 to yp. Bob's job is to solve f of xi1 y1 to f of xi p yp. In the same round elimination framework, now it's changed a bit. Alice has a matrix of lots of instances. These are big instances. Bob is picking a column for everything in that column, Bob has a corresponding input. They have to solve F on all of those things. So instead of one F, they have to solve now P different Fs. Okay? And what we were proving here is that you need either omega PQ from Alice or omega P times CCR minus 1 of F in the remaining numbers. Okay? Either Alice is telling you a non-trivial information about every one of these bits or every one of these inputs, omega PQ. This is the number of things Alice has. Okay? Or your job is to solve P different problems. Okay? For every one of them, you have to pay the R minus 1 round communication complex. So it's kind of a direct sum. Okay? And the reason it's not as easy as doing a direct sum is that for this block of P different things, you can reveal a small of P bits. You can correlate them heavily with each other. So it's not clear that you can actually get a direct sum. But you can prove this. Okay. So now why something like that is good? Okay. I'm going to change this structure. I'm going to give lots of graphs to Alice, G1, 1, 2, G1, K, GQ, 1, 2, GQ, K. Then Bob gets lots of these things. G1, GP. Okay. So you're going to put these graphs, these groups of graphs next to each other. Previously, I had one G1 that I would embed in the graph. Now I'm picking PQ graph and put it inside another graph. And these are all on B vertices. So I'm picking PQ graphs on B vertices, and I put all of them together inside one graph. Okay. Now, similar to before, Bob, like this is one copy on the left. You have something like that on the right. Again, Bob knows he has to solve it for one column, one group of these graphs. So he will pick, this is the group I have to solve it for. I'll connect everyone else with each other. This part remains. So to solve the MIS of the entire graph, you have to find the MIS of this group. I want the MIS of this part to be giving me the MIS of every single one of things inside. That requires two things. These guys inside the group, they have to be vertex disjoint. Okay, so the graphs that I have inside the group, they are vertex disjoint. Vertex disjoint, which means that P times B has to be less than N. Also, I need the same inducedness property in a very strong form. This entire group, if I look at this induced subgraph here, should just be the collection of these groups. Why? Because I'm going to find an MIS of this induced subgraph. It should not contain any edge from anywhere else. So this induced part, each group is an induced object. Okay, so each group is induced. Now, if you do this, what you're going to get here is that suppose, so what is the constraint this guy is going to give you? Again, let's just look at the pairs of vertices inside these groups. Okay? These pairs are B squared size. So I will have Q B squared has to be less than N squared. Some constraint like this. I want to be very clear. This doesn't mean such an embedding is possible. I'm just ruling out the most obvious way of like ruling it out. Okay, I'm saying that the most obvious test of do I even have enough edge pair, like pairs of vertices in my graph, is going to tell me this. How many pairs of vertices do I need to put QP graphs, each on B vertices? These are all the pairs of vertices my graph should support. Just looking at the most obvious test that the previous argument already failed for that. So I want to check this. This is going to tell me that P has to be, let's be very generous again. P has to be N over B. Q has to be N over B. The lower bound that I get is PQ for this one, which is B squared. So my lower bound is minimum of N squared over B squared. N times B. So you do all of this. This is now something which is in the best case scenario is N to the 4th. So if you can find an embedding, if you can put all of these things inside the graph, where the most obvious test is not telling you that you are going to fail, you will get an N to the 4th order.
Is the state of the art?
In terms of algorithms,
Or lower bound?
yes, all of this is a state of the art. We didn't know even a 2-pass lower bound.
And the algorithm?
They're, up until today, I thought they will get N to the 4th also, but in Andrew's talk, I saw it's saying N root 10, so I have to check that. I think N root 10 seems to be the right thing. Okay. Just one thing now. The last part, I want to just convince you that how, like, what is the embedding here? Like, why you should be able to put those things in 5 minutes. And these are these magical graphs. Which is the fun part. If you're completely out of this thing, this part is now I'm just going to tell you the object that I need. Okay? You need a graph that has Q blocks. Each P subgraph, each block contains of P subgraphs on B vertices. And the blocks are induced. Okay. Means that if you look at the induced subgraph on that block, you will only see edges of these subgraphs. So you want to create a graph that looks like this. Let's look at the very simplest case. Just set B equal to 2. And for those parameters, we essentially need this to be roughly N. We need this to be roughly N. I want to have a graph that has these blocks has almost N block. Each block contains of induced these are vertex disjoint subgraphs. Induced vertex disjoint subgraphs of size 2. So my subgraphs are now an edge. Okay. What is a vertex? What is N vertex disjoint edges? It's a matching, no? Okay. So I'm asking for a graph that has roughly N induced matches. In its simplest form, set B equal to, you need such an object. You need an object that, you need a graph that has roughly N induced matchings of size N. Induced matching means that there are no edges between them. Okay, like if you look at the induced subgraph, it's only the match. How many of you have seen these graphs before? Good. So such graphs are called Rosso-Zameredi graphs. Okay, this is a Rosso-Zameredi graph. I'm going to just call it RS. There's this construction by Rosso and Zameredi. Yeah. that says you can create such a graph. You can create a graph where Q is omega n, and P is equal to n over 2 to the theta square root of it. You can have a very dense graph which still have such a property. Okay. And just to see why such a thing is very magical, try drawing such a graph on like 6 vertices. Just put 6 vertices on each side. And then try to, so set P equal 3. You want to have induced matchings of size 3. Okay? You can easily create something where Q is equal to 4. This is one of my induced matchings. Then I'll come here. This is another one. There are no edges here. You see this part of the graph, these are only its edges. This is another one. This is another. I can put 4 of them. Just try to create one with 5. Okay. And then try to extend it to something distance. Okay. Another way, try to change P with log n and try to prove that. So these are RS graphs. They exist. They've been used a lot in last couple of years, maybe last 10 years, to prove a streaming lower bounds. Okay, they're a very useful tool to use. Okay, but for our purpose, let's go back here. We don't need. This was the simplest case. We said B equal 2. What is B for us? What are these subgraphs? These are the instances we get from the R-1 round. Okay, we were picking R-1 round instances and put them inside the graph. Okay, so instead of having just an edge, you want to create a graph that you can embed some subgraph inside it and satisfy these inducedness properties. And it turns out you can do that as long as that subgraph has certain properties. Like we need some minimal set of properties because we don't know how these hard instances will look like really. They'll become very complicated. But we also, like I think you cannot put a clique here, for instance. If you ask these guys to be a clique, probably you cannot create something good. Okay? But what we were saying is that for a k-colorable graph, the vertices, you can set Q to be 1 over B roughly. Maybe more specific. Both Q and P can be this quantity. Omega n over B divided by 2 to the delta log k log. So you can have a graph which has a size roughly like this. It's n over b divided by n to the small of 1, as long as k is not very large. If you create this graph, then you can do the embedding. Then you'll go through these arguments to prove the lower. Good. I think I've lost everyone at least 10 minutes ago, so I will just wrap up with the one-line quick conclusion.
Just another dumb question. So if you were just to take a random graph, I think not have those.
Yeah, random graph will be very far from this property. Oh, I should have said this construction is based on AP 3-term arithmetic progression free sets. And let me say, we are using for this construction, basically, there are extension of those 3-term arithmetic progression free sets based on k-term free, KAP free sets. We are picking those graphs. They have very nice properties. They have induced paths instead of having induced matching. Okay. In fact, they're stronger than just induced path. Okay. We're happy to talk about that offline, but you pick those graphs, and then you do a graph product to embed a k-color graph inside those sets.
So is it the case that the lower bound that you could get with these ideas are only for deterministic?
No, all of this is randomized.
That it seems that you're like picking very worst case.
This is for the embedding part. This graph is fixed. There is no randomness needed for this graph. All the randomness comes from what is put inside these subgraphs. Okay, so you're completely right. This is the skeleton is completely fixed. But inside these subgraphs, I can put whatever I want, and that's enough random.
And what if I want like hardness under the like a uniform random, like a Erdős random graph?
Oh, so on the random graph, these problems tend to be very easy. I don't know about MIS exactly. I would think you should be able to solve it in the log and communication.
So what role does K play in this calculation you showed?
Good. So, you know, I pick one, like in the one round instance, I had like 2 of these things. Then I picked all of that. All of these things become one of these subgraphs and go inside something like itself, being copied twice. So every time when you go from round 1 to round 2, you're increasing the number of levels by like you exponentiate, basically. So if I'm proving a log n round lower bound, at that point, my graph is going to have roughly log n layers. Okay. And those log n layers are like the colorability of the graph, which that's the K I'll get here. This construction should be able to handle very long graphs. But it's not that long, so that part is not going to bother us here. Yes. Okay.
Can you say which part dictates the log n?
Oh, good. Okay, so now you recurse on this construction. So this was for 2 rounds. From yeah, so why the lower bound is log n. So you keep doing these things recursively. I went from n square to n to the 4/3 for 2 rounds. In general, in R rounds, you go to n to the 1 plus 1 over 2 to the theta. The way the parameters work, this thing. If you write it like that, instead of b squared, like instead of n, this was n b squared. So instead of b squared, you have a 2-round lower bound. So now it's n to the b 4/3. This is the type of dependence on R you're getting, which together. Okay. 2 seconds. The final punchline was that for MIS in semi-streaming, the answer is theta log n passes. And let me stop with 2 open questions in this area, which I think are super nice. One open question is ST reachability. Can we prove better than, much larger than log n pass lower bound? And the other one, 1 plus epsilon approximate matching. Can we prove better than log 1 over epsilon passes? The state of the art are these 2 numbers, okay? And we seem to be really stuck. This has been there since work of Guruswamy and Onak in 2013. We figured out a slightly better bounds before log n, but here it's stuck at that for like more than 10 years. This is more recent, but still this seems very off from the current answer, the correct answer. Improving any of this is like really the main open question, I think, in this area. All right, thank you.
What are the upper bounds for?
For this one is n to the square root n passes. For this one is 1 over epsilon square for bipartite graphs, and log n over epsilon for all graphs, and wholly 1 over epsilon, which officially I think 1 over epsilon to the 19 for general graphs, but might be a bit better.
So the row one you showed gives a log n, which is tight by that result, but are the intermediary steps tight as well?
Yes, so I thought they're like completely tight. They might be off by a factor 2 here. So they might be slightly off in the number here. If you do it for 2 players, they will definitely be off. We did it for R players, so it becomes a bit closer to streaming. But I think even there it will be a bit off.
Any other questions? Okay, so if not, let's accept it.